Hello everyone. In this video, we're going to talk about ideal gases. So let's learn the concept of ideal gases and talk about the ideal gas law, okay? Also stay tuned until the end because we're going to solve a practical example. Alright, so let's start talking about what is an ideal gas. Well, in an ideal gas, the collisions between atoms and molecules can be ignored, okay? Also, because of this, we're considering that the molecules in an ideal gas are widely separated, okay? If they're widely separated, well, we can neglect the collisions and the forces between them, okay? So for an ideal gas, the forces between them are quite weak. Because of these assumptions, okay, for an ideal gas, all the properties depend on the number of atoms per unit volume and on temperature. So it depends on number of atoms, volume, and temperature. All the properties of an ideal gas. Okay, it makes our calculations and our problems much easier if we consider ideal gases. Now that we set the assumptions for an ideal gas, let's talk about the ideal gas law. This is the formula of the ideal gas law, okay? In this case here, P is the absolute pressure of a gas, V is the volume the gas occupies, N is the number of atoms and molecules in the gas, T is the absolute temperature, okay? This letter K here is a constant that we call the Boltzmann constant for the ideal gas, okay? So see that the pressure of a gas depends on the volume, number of atoms, and temperature. Okay, these are the variables we have only. If we plot P versus V, we have something like this. Okay, so P is a constant over V for this line here. If we have a fixed temperature, okay, this is a constant temperature line, we would have something like this. So for a constant temperature, we can define our P and V based on the number of atoms, okay? Now let's talk about the ideal gas law, but using moles. We generally use more this equation than the other one, okay? But first, let's remember the concept of mole. So a mole is the amount of substance that contains as many atoms or molecules as there are atoms in exactly 12 grams of carbon-12. Also, let's remember what is the Avogadro's number. That's the actual number of atoms or molecules in 1 mole, okay? And it's a constant. So now let's change our previous equation a little bit, okay? We can take this right-hand side here, multiply it and divide by the Avogadro's number, okay? And well, now that we have that n, the number of atoms or molecules, divided by the Avogadro number, is actually the number of moles, okay? And Na times K is what we call the universal gas constant R. We can calculate this R over here. So we have the Avogadro number and we have our Boltzmann constant. Okay, we're just multiplying two constants and it gives us 8.31 joules per mole Kelvin. Okay, this is the universal gas constant. Now, well, we have that N over Na is the number of moles, small n here, and Na times K is our universal gas constant. Okay, we generally use this formula here when solving problems because it's easier to talk about in gases, to talk about gases in terms of moles, okay, instead of number of molecules, right? So moles is much useful, okay? Okay, now that you learned all those formulas, let's put them to practice. So we have an airplane passenger that has 100 cubic centimeters of air in his stomach just before the plane takes off from a sea-level airport. We want to know what volume will the air have at cruising altitude if cabin pressure drops to 7.5 times 10 to the 4th newtons per meter squared. Okay, we can consider air as an ideal gas, so we can use the ideal gas law. We have P1, that's the atmospheric pressure at sea level, right, times V1 in his stomach equals nRT1. And after pressure drops, we have P2, V2, nRT2. For this process, let's consider a constant temperature, okay? We're just changing the pressure and the volume here. So we have P1, V1 equals nRT, P2, V2 equals nRT. So it means this thing equals this thing. P1, V1 equals P2, V2. Well, now we can isolate V2 and insert the values. We have the pressure, the atmospheric pressure at sea level here. Okay, we have V1, 100 cubic centimeters, and we have the pressure number 2. We can calculate the pressure here, it's around 135 cubic centimeters. So see that for a constant temperature, we lower our pressure, right? And then we expand the gas inside the passenger's stomach, okay? Because we are lowering the pressure, we're increasing the volume. Now I have a question for you. Under what circumstances would you expect a gas to behave significantly differently than predicted by the ideal gas law? So think about it under what circumstances and write your answers in the comment sections.
Now that you watched this video, you're one step closer to achieving your academic goals. Well done, well done! There's always more to learn, so check out our other videos and don't forget to subscribe.